Hello and welcome. This is Noah, and in this video we are going to look at an application of a rational function in order to introduce what rational functions are. For this example, we're going to look at a scenario where the concentration of a drug in a patient's bloodstream in milligrams per liter can be modeled by the function c of t equals 9t divided by t squared plus 6. Where t is the number of hours since the drug is injected. Real quick before I go any further here, I'm just going to make a couple of notes. The output of this function, output, is concentration, and that's in milligrams per liter. So just keeping track of our units. The input is time, and that's in hours. Keep track of that. Also, this is our example of a rational function. There are a lot of different rational functions, but rational function is something like r of x equals r for rational. Where we have a fraction, right? And there are some rules for how this goes, but we'll say that the top and bottom, whatever they are, these are both going to be just pretty standard functions. Polynomial functions is the formal name, but just like linear or quadratic are the kinds of things that we're going to see for this class. So where p and q are polynomials. And for this class, P and Q will be linear or quadratic. And we'll get into more details of what a polynomial is and how that applies to defining a rational function in later videos. So for now, let's just do an introduction, take a look at this specific one and see what it looks like to kind of get an idea of what some of these graphs might look like and be able to answer some questions. So as we move forward in the instructions, it says to graph the function using GeoGebra. So we'll do that in a minute. And then answer the following questions. What is the concentration after 10 hours? After how many hours will the drug's concentration be a maximum, and what is that maximum? And then finally, what happens to the concentration as time continues forward? So to answer these questions, let's just start with the part where we graph the function using GeoGebra. I have that pulled up here. So here I've got my GeoGebra, and there we go. So I can see both of these at the same time. C of t equals 9t on top, t to the second plus 6 on the bottom. And this is interesting. We've got some symmetry to this graph. That's kind of cool. We're not going to investigate that today, but that is something to be noted. In Math 111, you'll talk about that symmetry. It's called odd symmetry. And for our scenario, well, let's zoom out and take a look. Looks like as it goes backwards, it's all negative y values for all these points, and they're getting closer and closer to 0. And then as we move out to the right, they're all positive y values, or positive outputs, the positive outputs being the concentrations. And so we see that concentration is peaking right in there, right? Time 0, there's nothing in the blood, and then it goes up, and then it peaks right here, and then that concentration tapers off and it gets closer and closer to 0, right? So we could think of this as, as we're thinking about the concentration of a drug in a patient's bloodstream. So when you first inject the drug into the person's bloodstream, there isn't any of that drug, and it slowly seeps throughout the body's system and into that bloodstream, and then it maxes out. And as this is happening, the kidneys and the liver and everything are processing that drug and kind of removing it from the body slowly. And so we see that drug amount goes down and is exiting the body and gets closer and closer to 0. So let's go ahead and take just a screenshot of this so we can see. It's a bit bigger here. Oh, I'm going to actually add. If I do a maximum between 0 and 6, that should give us. No, that's not what I want here. I just want this point to stay. Extremum is what they want to use. C, start value, say 0, and value, you could say 6, because I know it's past that. There we go. And then I can get this to show the value. I don't need the A there. All right, now take a screenshot. Cool. Come back over here. There we go. So we want to know what's the concentration after 10 hours. So that's this point right here. And let's do that by hand. We can say, what is C of 10, right? The concentration after 10 hours. What we need is that the time t is 10. So we'll say C of 10, right? We plug 10 in for t. So we'll get 9 times 10 over 10 squared plus 6. And this will give us 90 over 106. Should always reduce our fractions here. We could do, both of them can be divided by 2, so 45 over 53. And if we got a decimal, decimals are actually nice for concentrations, and that's pretty standard in the field to be reporting that way because you can think of it as percentages. So if I should grab my GeoGebra up again real quick, and I could oops. This way, grab a scientific calculator and just type in 5 divided by 53, and we get 0.849. So approximately 0.849. So the concentration after 10 hours is about 0.849 milligrams per liter of the particular drug that is being used for this patient. Next question we're looking at is, after how many hours will the drug's concentration be a maximum, and what is that maximum? So that's this point that we are looking at here. So the maximum concentration is about, now keep in mind the outputs, the y values of the graph are the concentration, the inputs are the time. So this is the concentration in milligrams per liter, and this is the time in hours. So the maximum concentration is about 1.837 milligrams per liter, about 2.45 hours after injection. Cool. And then finally we ask what happens to the concentration as time continues forward. So as we go out to the right on this graph, we see that the concentrations are getting less and less. So we can say as time continues forward, the concentration of the drug is decreasing towards, so we see it's decreasing, but also we can say it's decreasing towards 0 milligrams per liter, right? And that's what we would expect here. So this is nice. It models nicely what we might expect to see for a blood concentration in a human body, where we see that concentration goes up. It hits a maximum after that drug has been kind of infused into that person's body and has circulated through it. But as it's circulating, the body is also processing that drug and working to remove it. And so we see that that will go down over time and, remove it completely eventually. It's decreasing towards 0 as time moves on. So we see that this graph, this function, does a nice job of modeling that kind of behavior. Now, not all rational functions look like this. This is just our first example. You'll go ahead and look at another example for the Now You Try. Go ahead and give that one a shot, and in the next video, we'll walk through that solution. Thanks so much for watching. We'll see you soon.